So shall we start it?
Yes, sir. You can
Okay.
start.
Yeah. When the going gets tough, the tough gets tough. And when the tough gets tough, they get StatQuest. If you haven't heard of the above lyrics before, which is one of the popular line in the Grammy worthy, don't worry. We bring to you the man himself, the man behind the StatQuest. Knock knock. Who's there? Bam! Is none other Joe Starmer, founder and CEO, StarQuest, the Chapel Hills, North Carolina. Seeking the blessings of Almighty, a very good evening to one and all. I, Shashankian, Assistant Professor in the Department of Computer Science and Engineering, Vidyavardhaka College of Engineering, Mysuru, extend a very warm welcome to you all for this international webinar on Learn Statistics for Data Science. First and foremost, I take this opportunity to welcome our resource person who is a multi-talented, multifaceted, versatile personality, Shri Joshua Starmer, founder and CEO at StarQuest with Joe Starmer, Chapel Hill, North Carolina. I welcome you, sir.
Thank you very much. I'm glad to be here.
I also take this opportunity to welcome all the enthusiastic participants across the globe who have joined this live streaming of the webinar. I welcome you all. It gives me
Hello.
immense it gives me immense pleasure about introducing the today's guest speaker, Sri Joshua Sharma, one of the most versatile personality, multi-talented, multifaceted musician, composer, and YouTuber who is having a followers of 304K subscribers. That's really fantastic, actually. He created StarQuest videos for YouTube, writes and records songs, instrumental music that has been commissioned by the dance companies and also got license for usage in the television commercials and also got featured even in the movies also. So coming to his education, he has completed his bachelor's degree from Orlean College and also completed his bachelor's degree in music theory in composition in the year 1999. And he has obtained his doctoral degree from North Carolina State University in the year 2016 in biomathematics, bioinformatics, and computational biology. In the year 2020, February, he became the founder and the CEO of StarQuest with Joe Starmer. Before this, he is having 13 years of experience in the teaching field. 7 years he worked as assistant professor in the University of North Carolina at Chapel Hill, a postdoctoral fellow for a tenure of 6 years, StatQuest founder for where he worked as the head of software development for 4 years, a musician, composer, and performer for 1 year. Sir, we are really fortunate enough as the resource person for this webinar on Learn Statistics through Data Science. Now it's time for you to start the session. I request you to take over the session. Thank you. Thank you so much, sir.
All right, here we go. Let's get started. StatQuest. Linear regression. Super cool. Yes, StatQuest. Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to be talking about linear regression. This is a classic StatQuest. This is one of the first ones I made. Some of you guys may not know the history of my YouTube channel, but it started out really as me just trying to help some of my coworkers. I used to work in a genetics lab, and the people in the genetics lab, they did great experiments, but they didn't really know how to do statistics. So I made this presentation for them. And now I get to give it for you as well. So hopefully it'll help you as much as it helped them understand linear regression. Okay, so imagine we collected weight and size measurements from a bunch of mice. Just looking at the data, it appears that heavier mice are also larger mice, and lighter mice are smaller mice. And overall, the trend follows this line. Now that we have the trend line, we can use it to make predictions. For example, if someone said they had a mouse that weighed this much, then we can use the line to predict that the mouse is this size. However, how good is this prediction? And why do we use this trend line and not some other trend line? These questions, how good is the prediction and what is the best trend line, is what linear regression is all about. So let's start by talking about how to pick the best fitting line. First, draw a horizontal line through the data. Second, measure the distance from the line to the data, square each distance, and then add them up. Terminology alert, oh no. The distance from a line to a data point is called a residual. So what we do here is we're basically measuring the residuals, the distances between the line and the data, then we're squaring those distances, and then we're adding them all up. Now we're going to rotate this line a little bit. And with the new line, we're going to measure residuals, square them, and then sum up the squares, just like we did before. Then we're going to rotate the line a little bit more, and then sum up the squared residuals. And after a bunch of rotations, you can plot the sum of squared residuals and the corresponding rotation. So on the x-axis down below, we've got different rotations. And on the y-axis, over on the left side, we've got the sum of the squared residuals for each one of these rotations. And then we find the rotation that has the least sum of squares. This rotation is the one with the least squares, so it will be the one we fit to the data. Note, in practice, we solve for the least squares line by plugging the data into an equation rather than manually rotating the line and adding everything up like I just showed you. However, I think the concept of what I showed you is the most important aspect. The equation, I'll be honest, I've been doing linear regression now for 20 years, and I can't remember the equation off the top of my head. However, I can remember these concepts, and it's just important to know that what we've done is we've rotated this line around, and we found the one that had the minimal sum of the squared residuals around it, and that's the line we're going to use. Anyway, regardless of how we determine the least squares line, this is it with the original data. Bam! Now we know why the method for fitting a line is called least squares. Now that we fit the line to the data, this is awesome. Here's the equation for the line. Least squares estimated two parameters. It estimated a y-axis intercept, that's 0.1, and it estimated the slope. Since the slope is not 0, in this case, the slope is 0.78. So since it's not 0, it means that knowing a mouse's weight will help us make a guess about that mouse's size. The question is how good is that guess? Calculating r squared is the first step in determining how good that guess will be. Note, I have a StatQuest already. It's a video online. You can go check it out. It's on YouTube, and it's on r squared explained. And guess what it talks about? It talks about r squared. However, we're going to do a really quick review because we don't have time to get on the internet and watch a video in the middle of my presentation. So let's just do a really quick review. Okay, the first thing what we're going to do is we're going to calculate the average mouse size. So we're going to take all of our measurements and we're going to collapse them on the y-axis, which represents mouse size. Here we've shifted all the data points to the x-axis to emphasize that, at this point, we're only interested in mouse size. We're not interested in mouse weight right now. The average mouse size is right here. Bam. Now we're going to sum the squared residuals. Just like in least squares, we measure the distance from the mean to the data point and square it, and then add those squares together. Terminology alert. Oh no. We're going to call this SS mean for sum of squares around the mean. Note, the sum of the squares around the mean equals the sum of the squared differences between the data and the mean. Now the variation around the mean, or the variance around the mean, is that sum of the squared differences between the data and the mean divided by n. And in this case, n is the sample size, which equals 9, because we measured 9 different mice. We've got 9 different reddish circles on the y-axis. So we can rewrite the variance of the mean as just the sum of the squares around the mean divided by n, or divided by the sample size. And another way to think about variance is the average squared difference. And I misspelled squared, so I'm embarrassed. Okay, now let's go back to the original plot and sum up the squared residuals around our least squares fit. We'll call this the sum of the squares around the fit for the sum of the squares around the fit, or SS fit. SS fit, or the sum of the squares around the least squares fit, is the sum of the squared differences between the data and the line. Just like with the mean, the variance around the fit, or the variance around fit, is the sum of the squared differences between the data and the line divided by n, the sample size. And we can rewrite that as the variance around the fit equals the sum of the squares around the fit divided by the sample size n. Again, we can think of the variance around the fit as the average squared difference. In general, the variance around something, whatever it is, it could be a fitted line or a fitted plane or some other weird shape. Whatever it is we want to calculate the variance around, we calculate the sum of the squared of those residuals, and we divide it by the number of things, number of observations, the number of data points. And that gives us the average sum of the squares. Okay, so this is the variation in mouse size around the mean. And this is the variation in mouse size around the least squares line. There is less variation around the least squares line than around the mean. Thus, we say that some of the variation in mouse size is explained by taking mouse weight into account. You'll notice that not all of the variation in mouse size is explained by taking mouse weight into account, because we still have residuals around the fitted line. Anyways, we see that heavier mice are bigger and lighter mice are smaller. So weight gives us some insight into what mouse size is. R squared tells us how much of the variation in mouse size can be explained by taking mouse weight into account. So here's the equation for R squared. Don't freak out. We're going to go through it one piece at a time. We get the variation around the mean minus the variation around the fit divided by the variation around the mean. For example, if the variation around the mean is 11.1 and the variation around the fitted line is 4.4, then we can plug those numbers in and we get R squared equals 0.6. In other words, R squared equals 60%. Thus, there's a 60% reduction in variance when we take mouse weight into account. In other words, those blue dotted lines around the mean get 60% smaller when we look around the fitted line that is using mouse weight. So we see those dotted blue lines are 60% shorter. Alternatively, we can say that the mouse weight explains 60% of the variation in mouse size. Oh, by the way, it's not that the blue lines themselves, it's actually the squared blue lines is 60% less. Note, we can also use the sum of squares to make the same calculation. So right now we're calculating r squared with variation, but remember, variation is calculated from sums of squares divided by the sample size. And if you look, that means we're dividing all of the sum of the squares by the same denominator, n, the number of observations, which means we can remove n and we end up with just the sums of the squares. For example, if the sums of the squares around the mean is 100 and the sum of the squares around the fitted line is 40, we plug in the numbers and we get r squared equals 0.6, which equals 60%, which is the exact same thing we got when we used variation instead of the sum of squares. So what I'm trying to point out is that there's two ways to get to the same number. We can either use variances or just the raw sum of squares, because the sample size does not change. Okay, so what we can say is 60% of the sums of squares of the mouse can be explained by mouse weight. Here's another example. We're back to using variances, but just imagine this could be sums of squares. Either way, we're going to get the same result. So now in this example, knowing mouse weight means you can make a perfect prediction of mouse size. So here are our values, our variances. We have on the left side, we've got the variation around the mean is 11.1. And on the right side, we've got the variation around the fit is 0. We plug those numbers in, and we get r squared equals 1, which equals 100%. And what that means is that mouse weight explains 100% of the variation in mouse size. Those blue dotted bars, they're gone when we use the fitted line. So we have no more residuals. Okay, here's one last example. In this case, knowing mouse weight doesn't help us predict mouse size. Heavy mice are both large and small. And light mice are also both large and small. So knowing mouse weight doesn't really tell us if the mouse is large or small, because heavy or light mice can be large or small. This is just a made-up example to illustrate this concept, not real data. So don't freak out. Okay, so here are our variances around the mean, 11.1 as always. And now our variance around the fit is 11.1 as well. So they're both the same. Now we plug in the numbers and we get 0 because the numerator, 11.1 minus 11.1 is 0. So r squared is 0%. And that tells us that mouse weight doesn't explain any of the variation in size. Okay, note, when calculating the sum of the squares around the mean, we collapse the points onto the y-axis just to emphasize the fact that we're ignoring mouse weight. However, we could just draw a line with this equation, y equals the mean of mouse size instead. And we can just calculate the sum of the squares around that mean if we wanted to. And the graphic on the right side of the screen is probably what we'll use from here on out. However, just know that they represent the same thing. This is the variation, or the sums of the squares, around the mean mouse size. Bam. Okay, So in this example, we applied r squared to a simple equation for a line. And we got r squared equals 60%. But the concept applies to any equation, no matter how complicated. 1, we measure, square, and sum the distances from the data to the mean. 2, we measure, square, and sum the distances from the data to whatever the complicated equation is. So let's look at a slightly more complicated example. Imagine we wanted to know if mouse weight and tail length did a good job predicting the length of the mouse's body. So we measured weight, tail length, and body length from a bunch of mice and plotted this data on a 3-dimensional graph. We want to know how well weight and tail length predict body length. The first mouse we measured had weight equals 2.1 and tail length equals 1.3 and body length equals 2.5. And likewise, just to spare us having me to plot every single point, this is what all the data looks like on the graph. The larger circles or balls or whatever are supposed to look like they're closer to us on the z-axis. The z-axis is the one that kind of goes back. That's the tail length, okay? So the further away or the larger the tail length, the further away they're going to be, and the smaller that circle's going to be. Yeah, unfortunately, drawing 3D graphs is not my strength. So hopefully this makes sense to you guys. Okay, now we do a least squares fit. However, we have the extra term for the equation. So instead of fitting a line to the data, we're fitting a plane. Because we've got 3-dimensional data, we can fit a 2-dimensional plane to it. And this is the equation for our plane. Y equals 0.1 plus 0.7 times x, which is the x-axis, or the value on the x-axis, plus 0.5 times z, which is the value on the z-axis. And we'll talk more about that in a second, so don't freak out if that doesn't make any sense to you. So y, the y-axis, represents body length. And these are 3 parameters estimated by least squares. We've got the y-axis intercept, just like we had before. X equals weight, so the x-axis is where we're going to plot mouse weight. And the z-axis, the one that's going back, that's the one that we use to plot tail length. If we know a mouse's weight and tail length, we can use the equation to guess the body length. For example, given the weight and tail length for this mouse, the equation predicts that this is the body length. And just like before, we can measure the residuals, square them, and add them up to calculate the r squared. So you see, in this example, what we see is that the predicted body length is actually different from the actual or known body length. And that just means that this plane doesn't fit the data perfectly. All it does is it's trying to minimize those square differences. So it's not a perfect fit. And that means the predictions will not be perfect, but that's okay. It's just sort of what it is. So don't worry about that too much right now. Note, if the tail length, the z-axis, the one going back, if it's useless and it doesn't make the sum of the squares fit any smaller, then least squares will ignore it by making that parameter equal to 0. In this case, plugging in tail length into the equation would have no effect on predicting mouse size. We could plug in 10 for tail length, and once we multiplied it by 0, we'd get 0. We could put 2 in for tail length, and we'd still get 0 because we're multiplying it by 0. So what that parameter equals 0 does is it says tail length, is not useful. If tail length is useful, then we'll get a non-zero value for that parameter. We'll get 1.3 or 2.4. And that means when we plug in a tail length, it'll make a difference in the y or the estimated body length. However, in this case, we're just assuming that tail length plays no role in predicting body length, so the parameter is set to 0. And what this means is that equations with more parameters will never make the sum of the squares around the fitted line or the fitted plane worse than equations with fewer parameters. Now, let me show you what this means. Okay, in other words, this equation where we have mouse size equals 0.3 plus mouse weight, which we've already seen is very useful, and then we add in all these things that are useless, like flipping a coin, favorite color, astrological sign, ... Lots of things that may not help us predict mouse size. This equation will never perform worse than this equation. Mouse size equals 0.3 plus mouse weight. And that's because least squares will cause any term that makes the sum of the squares fit worse. It'll make those coefficients or those parameter values equal to 0. And so flipping a coin, if that's not helpful, we're going to measure the heads or tails by 0, and it's going to that term will turn 0 no matter what. If favorite color is not helpful, we're going to multiply it by 0, and it'll just be 0 all the time no matter what, and it will not affect our prediction of mouse size. Now, due to totally random chance, there's a small probability that small mice in the data set might get more heads more frequently than large mice. This is just random chance. Say like every time we weighed a mouse, we flipped a coin and we recorded whether we got heads or tails. Okay. Now, we know on average we're going to get heads and tails 50% of the time, but every now and then we might get 2 or 3 heads in a row, or we might get 2 or 3 tails in a row. And it just might be that when we measured 9 mice, maybe we got heads 6 of those 9 times, and we only got tails 3 of those 9 times. So generally speaking, heads is more frequently associated with small mice. If this happened, we'd get a smaller sum of squares fit, because including this coin flip would improve our ability to predict the mouse size. We'd say, oh, if it's heads, there's a better chance it's going to be a small mouse. And that's going to give us a better R squared. And that's no good. We don't want random stuff making us think that we're doing a good job predicting, because if we kept flipping that coin, overall, we'd see that getting heads and tails has no relationship to the mouse size. And so that's, in the long term, not going to help us make predictions. And so that's no good. And the more parameters we add to the equation, the more opportunities we have for random events to reduce the sum of squared fit and result in a better R squared. And this is just terrible. Thus, the good news is people report something called an adjusted R squared. So if you ever do a regression analysis, oftentimes you will see returned is a value for something called an adjusted R squared. And all that means is that it's an R squared adjusted for the number of parameters. So the more parameters you add, it penalizes your R squared just a small amount, with the assumption that there's a chance that it could be that random stuff that's not actually related to mouse size is actually, given this small data set, helping us predict mouse size. Okay, R squared is totally awesome. I love it. So should you. But it's missing something. Okay, so what if all we had were 2 measurements? Well, we can calculate the sum of the squares around the mean, and in this case, we get 10. But when we calculate the sum of squares around the fit, we get 0. The sum of the squares around the fit is 0 because you can always draw a straight line that connects any 2 points. So here we're just going to plug in the numbers, and we're going to calculate R squared. So we got and so we see that we got 100%. And that's a great R squared. but basically any two random points will give us the same thing. If you notice in the math, there's a slight typo. I've got 100 minus 0 divided by 100. It should be 10 minus 0 divided by 100. Unless, I guess I'm using variances in which, well, that would be even smaller. Anyways, there's a slight typo, but you get the idea. We're going to get, if we plugged in 10 for 100, we'd still get 100%. I apologize for the typo. Anyways, here are two other randomly drawn points, and the r-squared value is 100% again. And here it is, r-squared equals 100%. Just two random points. We could draw any two random points, whatever, with our eyes closed, and we'd still get an r-squared of 100%. So what does this tell us? It tells us we need a way to determine if that r-squared value is statistically significant. Because sure, any two random points can give us an r-squared of 100%, but if it's not statistically significant, then we're going to say no big deal. But if we get an r-squared and it's statistically significant, we'll say, oh, let's pay attention to this. Okay, so we need both of these values. And that means we need a p-value. Okay, before we calculate the p-value, I just want to review the main concepts behind r-squared one last time. Okay, r-squared is the variation around the mean minus the variation around the fit divided by the variation around the mean. In other words, in this example, we've got the variation around mouse size minus the variation after taking weight into account divided by the variation around mouse size, alone without taking weight into account. In other words, r-squared is the variation in mouse size explained by weight divided by the variation in mouse size without taking weight into account. In this particular example, r-squared equals 0.6, meaning we saw a 60% reduction in variance once we took the mouse weight into account. Now that we have a thorough understanding of the ideas behind r-squared, let's talk about the main ideas behind calculating a p-value for it. The p-value for r-squared comes from something called f. F equals the variation in mouse size explained by weight divided by the variation in mouse size not explained by weight. The numerators between f and r-squared are the same. In both cases, we're looking at the reduction in variance when we take weight into account. The denominator, however, is a little different. These dotted lines, the residuals, represent the variation that remains after fitting the line. This is the variation that is not explained by weight. So now let's look at the underlying mathematics. Just as a reminder, here's the equation for the r-squared. This is the equation that will tell us if r-squared is significant. This is the equation for f. The meat of these equations are very similar and rely on the same sums of squares. The numerators are the same. In our mouse size and weight example, the numerator is the variation in mouse size explained by weight. However, the denominator is a little different. And these numbers over here are degrees of freedom. They turn the sums of squares into variances because we're dividing those sums of squares by some number. So we're getting an average of the sums of squares per something. Note, one of these days, I'm going to dedicate a whole StatQuest to degrees of freedom. But for now, let's just see if we can get an intuitive feel for what they're doing here. We're going to start with these. P-fit is the number of parameters in the fitted line. So the fitted line is y equals the y-intercept plus the slope times x. X is the x-axis value. So we've got two parameters, and so p fit equals 2. P mean is the number of parameters in the mean line. And so the mean line is just y equals the y-intercept, or the mean value of what's on the y-axis. So we've only got one parameter over there, and that means p mean equals 1. In other words, both equations have a parameter for the y-intercept, but the fit line has one extra parameter, the slope. In our example, this slope is the relationship between weight and size. So we can subtract p mean from p fit. So that gives us 2 minus 1, which equals 1. And that tells us that the fitted line has one extra parameter, mouse weight. Thus, the numerator is the variance explained by the extra parameter, or in general parameters, but in this case, we just have one extra parameter. In our example, that's the variance in mouse size explained by mouse weight. If we had used mouse weight and tail length to explain variation, then we'd have 3 parameters in our equation, and p fit would be equal to 3. And when we do the math, we subtract p mean from p fit, we get 3 minus 1, and that gives us 2. And now the fit has 2 extra parameters, mouse weight and tail length. With the fancier fit, the numerator is the variance in mouse size explained, or the average explained by mouse weight or tail length, or the average per extra parameter. Okay, now let's talk about the denominator. The variation in the mouse. This graph shows the variation in mouse not explained by the fit. So we still have those blue dashed lines representing the residuals. The question is, why are we dividing by n minus p fit instead of just n? And intuitively, the more parameters you have in your equation, the more data you need to estimate those parameters. We need to estimate the intercept, and we need to estimate the slope. In this case, if we had a bigger or fancy equation, we'd need to estimate the intercept and the slope for each one of those extra parameters. So for example, in order to estimate the slope for a line, we need at least 2 data points. And those data points, once we have them, can't change. When we're estimating the slopes for a plane, we need, or the position of a plane, we need 3 data points. And in higher dimensions, we just need more data to be able to estimate the parameters. And so what we're doing right now is we're compensating for the fact that we had to estimate for a number of parameters. And the more parameters we have to estimate, the more we're sort of like compensating for that. We're subtracting data, so the average value is going to be, we're going to end up with a larger value in the denominator. Okay, so bam. Kind of wishy-washy, but just go with it. Okay, if the fit is good, then F, which is the variation explained by the extra parameters in the fit, divided by the variation not explained by the extra parameters in the fit. Okay, so that's what F is. Now, if the fit is good, then the numerator should be a large number, meaning that the fit should explain a lot of the variation in the original data, meaning those blue dashed lines should be much shorter around the fitted line or plane or whatever it is we're fitting to the data. So when those dotted lines are really short, the amount of variation that we've explained by the fit is a large value. And when those dotted lines are short, then the variation not explained by the parameters, by the plane or the line or whatever we're fitting to the data, that's a small number, because we're just squaring these relatively small dotted lines and adding them up. Okay, so we have a large number divided by a small number. That's when the fit is good. And that means F is going to be a really large number, because when you divide a large number by a small number, you end up with a big number. Okay, so the question is, how do we turn this number into a p-value that'll tell us whether or not our r squared is statistically significant? Well, here's one way we could do it. This isn't the way we do it in practice, but here's a way that we could do it to give you a conceptual understanding of what it means, okay? So what we could imagine doing is generating a set of random data and then calculating the mean and the sums of squares around the mean. And then we calculate the fit. So we do a least squares fit to this random data, and we calculate the sum of the squares around the fitted line. Then we calculate f for this random data. And that, in this case, we get f equals 2. And so we're going to plot this on a histogram of f values. Now we're going to generate another set of random data, calculate the mean and the sum of squares around the mean, and then calculate the fit and the sum of the squares around the fit, and then calculate the f value. And in this case, we get f equals 3, and we plot it on the histogram. And then we just keep doing this. We repeat with yet another set of random data. And then imagine just repeating and doing this with random data over and over again, and just generating this histogram of what happens when we use random data to calculate f. Now let's go back to the original data, which isn't random data, because there's a relationship between how weight is related to mouse size. Now we calculate the f for the original data, and we get f equals 6. So we're kind of out in the tail of that distribution, or that histogram. The p-value is the number of more extreme values divided by all of the values in that histogram. Bam. Note, in practice, we approximate this histogram with a line rather than generating tons and tons of random data sets. What we do is we use this line to calculate the p-value. So this is a picture of one F distribution, and the degrees of freedom, which is what we use to calculate F to begin with, these are the degrees of freedom, determine the shape of this curve. So here we've got P mean minus P fit equals 1, and N minus P fit equals 10. This is another curve. This red line is another curve with different degrees of freedom. In this case, we've got P mean minus P fit equals 1. So it's the same. That's the same as before. However, this time we've got less data. So N minus P fit equals 6. Notice that when N minus P fit equals 10, the distribution tapers off faster. This means the p-value will be smaller when there are more samples relative to the number of parameters in the fit equation. So basically, the more data you have, the smaller your p-value will probably be. Triple bam. All right, let's go over the main ideas. Given some data that you think are related, linear regression quantifies the relationship in the data. This is R squared, and you want this to be large. 2, it determines how reliable that relationship is. And this is the p-value we calculate with F, and this needs to be small. You need both to have an interesting result. So if you have a really small R squared and a really big p-value, then we don't care at all. If we have a very big R squared and a really small p-value, then we get really excited. So that's it. Hooray! We've made it to the end of another StatQuest. I'm under the impression that now we have some question and answer session. So I'm going to stop sharing, and now you can see me big and large. Hello. Anyways, I'm under the impression we can have question and answers now. So if anyone has questions, please ask them. I don't know if there's a moderator for these questions or not. And I don't actually know how questions are even asked. I don't know if you can put them in the chat or the comments. Okay, looks like we're back.
Yes, sir, actually. Sir, it was indeed a very nice session, actually, on this exciting topic.
Thank you. Yeah, thank
sir,
you very
actually,
much.
there is one question.
Yeah?
Can someone from a non-statistical background study these topics?
Of course. Yeah. I think, if they're properly explained, these concepts can be explained to anybody. It doesn't matter what their background is. Now, explaining things isn't necessarily a talent that I have. It's a skill that I've developed over the years. And so I believe that some of my newer videos are probably better than some of my older videos because this is a skill I've acquired over time. So if this video was hard for you, just know that it's one of my earlier videos or earlier ones, and I hope I've improved over time. And you can check out some of my newer videos and go, oh, I get that instead. So it's just, I think anyone can understand this. Someone asked, it looks like I'm looking at the comments right now, and I see someone asked what concepts we should focus on to get into data science. I think the concept of variation is one of the biggest concepts you can possibly understand. Sum of squares. It's something that just pops up in every aspect of data science. It pops up in machine learning. It pops up in statistics. If you can understand variance, and you can understand that we can fit something to our data and that reduces the variance around that fit thing is smaller. If you can understand that concept, you probably understand 50% of all there is to know about machine learning and data science and statistics. So that's, I think, the most important concept, especially the concept of what statistic, and beyond that, I would say that it's important to know the concept of statistical significance, which is how to determine if something is just noise, just random chance, or if what you're looking at is a real signal or a real relationship. So,
Sir, one more question is there. How should we do the learning?
how should we do the learning? Any way that works for you. A lot of people learn different ways. Some people are really good with YouTube videos, and that's great for me because they watch my videos and that helps my channel. That's fantastic. Some people are very good with books. I'm actually, I don't know. Am I good with books? I don't actually think so. I'm very slow with books, but I tend to learn with books. So I get books and I read about stuff and I think about it and I sketch things out on my own. You have to figure out what your learning style is and then seek out material in that learning style. So if you're a visual learner, you need to find someone who teaches in a visual style. I teach in a visual style, so if that's your style, great. But if you're not a visual learner, some people are more drawn to looking at the raw equations and that helps them more. You need to find a teacher who's more prone to just using the equations and just find your own learning style and then find a way to learn within that learning style. Don't try to fight it too much. It's worth looking around to try to find if you can. That's the amazing thing about the internet is even though you're in one place in the world, like I'm in Chapel Hill, North Carolina, which is a very small town in the United States, kind of about halfway between New York and Miami, down the East Coast. and it's a small town, but that doesn't mean I can only use the people in my small town to learn stuff. I get on the internet and I look everywhere, and I look for every resource I can find. And I just try to, and I just look and I look and I look and I look and I look, and sooner or later I find something that I can understand. And then I go, okay, good, I got it now. And so I just say, be determined. And when the first thing you see doesn't make any sense at all, that's the way it is for me too. It doesn't make any sense to me, and I have to keep looking, and I have to keep searching, and sooner or later I'll find something that I can kind of understand, and then I can go back to that stuff that didn't make any sense to me to begin with, and maybe it makes a little more sense the second time. Maybe it doesn't. It doesn't matter. I'm just going to keep looking for stuff that makes sense to me. So that's my tip.
So one more question is there. Sir, how important the mathematics in data science is? Our professor and head, Dr. Ravi Kumar sir, has asked this question.
Yeah, I think it's a great question. And the answer is sort of depends on what you want to do. So as you saw earlier on, I was talking about the concepts of least squares and how we rotate this line. And when we rotate it, the sums of the squares of the residuals around that line changes. Okay, and we're searching for the rotated line that has the minimal sum of the squares of the residuals. Okay, I understand that concept, and I can remember that concept very well. However, the mathematics that's actually involved in least squares, I do not remember at all. However, I'm absolutely 100% confident that when I do a linear regression, I know how to interpret the results, I know how to understand what happened, and I know basically everything there is to know about it. The fact that I don't actually remember off the top of my head that equation for solving for the least squares estimates makes no difference in my ability to apply and use linear regression. Okay, so I can apply and I can use linear regression. However, can I extend linear regression? Can I add on to it and come up with a new methodology? Probably not, okay? So if I want to use linear regression, sure. What I need to know are the main concepts, the main ideas, the concepts of reducing variation around a fitted line versus sort of an unfit line where we're just using the mean. So if I just want to use linear regression, I need to understand those concepts. But if I want to create a new and better linear regression that's even cooler and more awesome, yeah, I'm going to need to know those mathematics. And I'm going to need to know how it works and all that so I can build on it. So it really depends on what you want to do. Do you want to be an innovator in the field of data science where you're creating new methodology? That's a cool thing to do. It's not for everyone. It's not for me. And then there's people that are more practitioners of data science. And if you're just a practitioner, I would say focus on the main ideas rather than the mathematical details. And that's perfectly all right. That's me. I love practicing data science. I'm not going to be the guy who invents the next cool method. So I feel like there's roles for both people, but the knowledge required are different. We don't all need to know the exact same things to be able to do these two very different jobs. Yeah.
So Python is our programming language. Which programming language to use for data science? That's the next question.
That's like the ultimate question, right? That's the eternal Python versus R. They're both very good. Obviously, Python is a general purpose language, and R is a language designed specifically for data science and statistical analysis. They both have pros and cons. If you know Python already because you've learned how to do, program video games, or you learned how to program a web browser or whatever, you may already know Python. You can do a lot of awesome data science in Python. In contrast, if you don't already know Python and you're not planning on becoming a general purpose programmer, you might want to think about R, because R is designed for data analysis. So it has a lot of built-in features that Python, because it's general purpose and isn't designed just for data science, R has a lot of cool features that are not built in for Python. So R has built-in handling of missing data, for example. Missing data is a big deal in data science. In R, it's super, super straightforward and easy to deal with missing data. It's also super easy. You know, all your functions are just built in. If you want to draw a histogram, you just type hist, bam, done. If you want to draw graphs, you just draw a graph, bam, done, no big deal. Whereas in Python, you got to import all those modules. You got to import a module to draw a histogram. You got to import a module to calculate a mean. So there's kind of like an overhead of extra typing. Every time you want to do something, you have to type NP for NumPy, or if you want to use scikit-learn, you got to type SK, you know, or however you're importing those packages. And in R, generally speaking, you just type it and it's no big deal. So the answer sort of is like, what kind of programmer are you? Are you strictly data analysis, data science, or are you more general purpose? I'll be honest, I'm a little bit of both. I do a ton of data science, and when I had my job at the University of North Carolina, that's all I did. So I did tons of R programming. But now I do more general purpose programming. And as a result, now I do a lot of Python. So it just sort of depends on what kind of programmer you want to be. So that's the answer to that question.
So how to minimize the linear loss in case of categorical data set efficiently?
How to minimize the linear loss in case of a categorical data set efficiently. I'm going to be totally honest. I don't actually understand this question. I don't understand the question. I don't know. I mean, I can take a guess. In linear models, like what we just did, linear regression is an example of a type of linear model. Linear models include the ability to use categorical data. And it ends up being the exact same thing. We end up calculating the residuals and the variances exactly the way we did it just before. So to give you an example, so in what we just did in linear regression, we looked at the variation in size relative to weight. However, we could have looked at variation in size relative to hair color. That would be categorical. We could do black or brown, blonde, or we could do, you know, variation in size with respect to different species. That would also be categorical. Okay. We can build out our model just like we did before. And actually, I've got StatQuest that follow up on what we just watched. So if you go to statquest.org, you can see how categorical data can be used to give us to help us make predictions about mouse size or whatever else we want to make predictions about. So I don't think I answered that question at all because I didn't understand it, but I tried to at least talk about categorical data. So maybe that was helpful. I don't know.
So if you want to learn statistics for the beginners, can you please suggest any books for that?
Unfortunately, I don't have any good references for books for statistics. They're all pretty bad, if you ask me. Yeah, I don't really know what to suggest. They're just all bad, in my opinion. That's just my opinion. I don't speak for everyone, and also don't speak for everybody's learning style. My personal learning style is very visual, and I just found a lot of statistics books sort of sometimes they try to be visual, but they're not very serious about it. They don't take it very seriously, and they focus a lot more on the equations, and that's not as useful for me. So my personal opinion is that I have not found any good statistics textbooks for basic statistics. However, you know, other people might have different opinions. So just ask around. I mean, I'm sure other people will say, oh, I really love this book. I just don't have any books I like.
Sir, any preferable courses in the new AI and ML engineering programs? Do you want to suggest any preferable courses?
I don't actually know. I don't know what I don't know what courses are. I don't know anything about these courses. I mean, I wish I could. I'm sure they're all great and awesome, and it sounds very exciting. But I don't know what the courses are, what you're offering, and I don't know anything about them. So I don't know if I can answer that question.
If you want to improve your skills in the data science as a practitioner, how it would be possible?
Practice, lots of practice. You just have to do it a ton to get familiar with it. It's like, I don't know if you're familiar with writing code, but when I was younger, I learned how to write and I learned how to program. And sure, I understood the concepts. But back then, if you were missing a semicolon or something like that, the whole program would fail. Okay. And to become a good coder wasn't necessarily that I learned how to code in fancier ways. Sure, I grew a little bit in that direction, but really what I got good at is being able to spot missing semicolons. Okay. And the only way I got good at that was just doing it a lot, because once you start realizing what are the common mistakes you make, what are the common little slip ups, you can debug what you're doing. You can improve on what you're doing much faster. And so just practice. What I like is there's a lot of data sets out there. IBM hosts some great data sets. Kaggle, there's a website called Kaggle that hosts some great websites. There's a website called the UC Davis Machine Learning Data Repository. It's fantastic. They have all these great data sets, and what they also have is great annotation that goes with the data set to give you an idea of what you might find in that data set. So you can download the data, start poking around with it, and see if you can't come up with the same results that the people came up with that put the data there. It's a great way to kind of learn and practice. Another thing is, and I found whenever something is nagging you, like you have a little voice in the back of your head says, am I certain about that? Always follow up on those questions and Google. I've often found I've learned a lot just by Googling little questions about what I'm doing. There's great discussions on something called Stack Exchange or cross-validated. I can't remember the name of it. I think Stack Exchange is sort of the most common website for it, but there's lots of great websites out there. Yeah. What else?
So there is actually one more question.
Okay.
Sir, how to go about doing predictive analysis with lots of labeled data?
Lots of labeled data. Is labeled data categorical data? I mean, in that case, you can just do linear regression with categorical data.
Test data available like that.
Unfortunately, the connection got really weird. I couldn't hear what you were saying. Can you repeat that?
Yes, sir. Sir, how to go about doing the predictive analysis with lot of labeled data when we have trained data as well as test data available?
Training data as well as test data. I see. Okay, I get. I still don't get the question. I'm going to be honest. I mean, you fit your model to your training data and then you validate it with the testing data. I don't really understand what they're getting at. I'm sorry.
Sir, actually, yes, sir, that is actually categorical as well as the numerical data.
Yeah, if you're mixing those things, no big deal. Yeah, sure. If you're mixing categorical and numerical data, you can do a linear model. Like I said, the follow-up videos, if you go to my website, statquest.org, there's a link in the menu bar for video index. And I would just scroll down. Actually, I've got a whole playlist on linear regression and linear models. Just watch all those videos in linear regression and linear models, and then you will learn everything there is to know about how to use those mixtures of categorical and continuous data to make predictions. And then once you understand that, when we're doing regression, we're predicting sort of continuous things like mouse size, right? And then, but once you understand that, then you can go to logistic regression, and then you can see how continuous and categorical data can predict sort of true or false, like yes, no, is the mouse obese or is it not obese? As opposed to how much does the mouse weigh? Weight would be continuous, and just is obese and not obese would be discrete. So what I would say is watch my playlist on linear regression and linear models, and then watch logistic regression, and then you will be enlightened and you'll know all those things. And I'll show you how to do it. Specifically, there's a real fancy trick called design matrices, and it shows you how to how to create and use design matrices. And that's sort of the essence of how to do complicated models with regression or logistic regression.
So one last question.
Okay.
What is the path to become a data scientist?
What is the path? I don't really know. I mean, I've always been interested in data science and computation. I'll tell you my path. I started out as a musician. I love music, as you can tell. I'm not the best singer or the best ukulele player in the world, but I love music. And when I grew up, I wanted to be a musician. And so I studied music like crazy, and I practiced. I used to play the cello. That's my ukulele. I love the ukulele. It's not my primary instrument. I grew up playing the cello, which is a big, huge instrument. It's kind of bass sounding. It's kind of, in some ways, it's a little bit like the Carnatic vina. I don't know if you're familiar with that. It's a big thing made out of jackfruit and has a big end on one side and a gourd kind of propped up on your knee. Maybe does it have a? Yeah, I think it has a small gourd. It propped up on your knee, and you kind of play it. Both instruments have 4 strings. Anyways, I played the cello like crazy. I was pretty good at it. But I could never get jobs in music. I mean, I did make some money. I've sold some music. I've done some television commercials. I've done some movies, and I've done some dance, some dance companies commissioned works for me. So I've done stuff, and that's fun and cool and awesome. But I'll be honest, I wasn't satisfied with that. You'd think I would be. It'd be great to be a musician, but I didn't really like it that much. And so I switched careers. I studied computer science. I studied programming, and then I studied something called bioinformatics, which is basically computer science applied to biological data. So that was my path. That's what got me into it. I came from a very different background, but it wasn't hard to make the transition. So what's your path? It could be anything. I would focus, however, on understanding basic statistics, understanding variation, understanding p-values and what they mean. Become familiar with at least Python or R, one of those 2 languages, up to you. And then just start plugging away. Maybe take some classes and learn about stuff, or maybe just watch tons of YouTube videos and learn what you can. There's so many resources out there and great ways to learn.
Sir, actually, there was one question asked. What are the preferable courses in our new AI and ML engineering program? To add a few sentences about this, in our college, from this current academic year, we are going to start a new engineering branch called Artificial Intelligence and Machine Learning. So in this context, according to you, or can you give any suggestions about any addition of new courses for this branch?
Oh, what classes should this branch offer?
Yeah.
I have no idea. I still don't have any idea. I mean, I guess courses in machine learning and artificial intelligence. I don't know. I mean, I'm terrible with this kind of stuff. I mean, yeah, I have no idea. I mean, it depends on what the goal is. What is the goal? What do you want the students to be able to do? What, when they graduate, what kind of jobs do you want them to have? If you can answer that question, we can start talking about what they need to learn. Do you want them to get jobs in banking? Well, maybe they should get some jobs in some classes in finance, or how data science applies, or machine learning or artificial intelligence applies to banking. Do you want the students to get jobs in sort of general purpose computing, or just general artificial intelligence? Well, I guess you want a course that kind of gives you overviews of artificial intelligence and sort of the methodologies that are very common. Maybe reviewing the boosting algorithms, and how they work, and neural networks and how they work. But it really depends on what you want the students to, what kind of jobs you want the students to have. And if you define that, then for me, it'd be easier to say, oh, there should be a course in this and a course in that. And, these are things that would lead to that direction. However, I will say that given all that, it's also good to just be flexible. Like you saw about me, I was a musician. Fortunately, I did not take only music classes, right? If I'd only taken music classes, it would have been hard for me to make a transition. So I think it's important to have sort of broad classes in terms of like how to program. Sure, we can learn, you can do a ton of stuff with R, but teach it not just towards here's how to get a linear regression, but here's just general programming techniques. Here's a for loop, here's a while loop, here's how to program in general. If you can do those things, you can bounce around from language to language, because learning a new language is a lot about just learning how you're going to do for loops in the new language. What's the syntax? Once you learn the syntax, then sure, you're going to pick up that new language really quickly, and that makes you flexible and it give you the ability to go from one field to another field. And I think there's some value in that, and not just being like locked into whatever you took your coursework into. So I guess as long as you give some specific examples of how things are done within a certain field, but then maybe instead of just saying, hey, we're going to do all these examples in the finance sector, maybe we're going to do one example in finance, and one example in biomedical engineering, and one example in some other field. I don't know. You name it. Geology, who knows? Yeah, maybe geology. And once you start seeing how these tools can be used in various contexts, well, then you would gain the ability to be flexible once you had to get a career. So even though I said whatever, they can teach whatever they want, now what I'm saying is, and now I've talked enough, and maybe I'm getting some sense in my head, and I'm thinking that what you want to do is teach, obviously a little bit of both. Give them specific examples of how these things are applied in different situations, so that the students can get a sense of, if I was in finance, I could do this. If I was in geology, I could do the same thing, just with different, numbers and different variables. Or if I was in biomedical engineering, I can do the same thing with numbers and different variables, different numbers and different variables. And then if something else new came at me, some new field, like aerospace engineering, I could say, hey, maybe I can do the same thing with different numbers and different variables. And I can say, yeah, I get a new job, even though I didn't specifically train for aerospace engineering. So there you go. I hope everyone had a great time today. Thank you very much. Hooray. Oh, it sounds like my answer was helpful. That's fantastic. Thank you. Thank you.
Sir, now the time has really come to wind up this session. From expressing the deep sense of gratitude on behalf of the Department of Computer Science and Engineering, VVCE Mysuru, I extend my hearty thankful to you, sir, for joining this live streaming of webinar. Thank you so much, sir. Thanks a lot for giving a valuable insight on this Learn Statistics for data science. Indeed, it was a very nice session. Thank you so much, sir. And I also thank all the participants.
Yeah,
I also thank all the participants Thank you, sir.
Yeah,
I also
thanks
thank
everyone
all
for
the
watching.
participants
Yeah.
who joined across the globe for this international webinar. Once again, thank you all. Thank you so much. Have great uh, have a great day. Learning is a continuous process. Stay safe, stay healthy. Once again, thank you all. Thank you so much.
Yep.
Signing off.
Okay. Goodbye.
Goodbye, sir.
Yep. Thanks.
We'll be in touch. Thank you, sir.